Well, it looks like a laminar flow, but what does that mean?
Hello, welcome to my tech farm. And yes, probably this is one of those videos where I will lose subscribers, but somehow I feel this pressure to create this video. Recently I was watching few videos about core and multicolor filaments, and I could see that not only the commenters, but sometimes even the creator itself is confused a little bit what a laminar flow means and what are the limitations. And myself also I want to check what is the limit. I mean, if in the future we increase the printing speed significantly, how will it affect this laminar flow? So I created this presentation. Let me know in the comments, is it too boring, too complex, or understandable? So let's start with it. First, I want to mention that this video and the whole channel is sponsored by Polymaker, who is supporting my research activity. Why laminar flow matters in 3D printing? Well, we have those dual or three-color filaments, and they have different colors in the cross-section, and we don't want those colors to be mixed during this flow and printing. Or for example, core filaments, they have the core structure, usually carbon fibers, and raw material outside. And after the printing, we want that printed line to have raw material outside and core only inside. Practical example shows that it is laminar, but how close is the limit? I mean, if we print something from these dual color filaments, we can see that one color is from one side and the other from the other side, so the color didn't mix. I'm sorry, I apologize for this, maybe professional deformation, but I can see quite often the expression like the plastic is laminar, which is very incorrect expression. So the more correct would be, let's say, the flow conditions of the molten plastic are laminar and not the plastic itself. Two examples of the laminar and turbulent flow of the water. And actually this can be calculated. Reynolds number is dimensionless number that describes the nature of the flow. Is it laminar or turbulent? And we have these limitations. There are some restrictions, but I'll explain this later. For now, let's remember this number, 2300. We will need it later. There are several equations for the calculation of the Reynolds number, but I will use this one. D is the inner diameter. V is the speed, but speed of the filament in the nozzle, not the traveling speed of the extruder. Density, and then divided by dynamic viscosity. Just to be clear roughly with the numbers, for the water it is 0.001 Pascal seconds, and for the honey on the room temperature it is around 10 Pascal seconds. Let's see the calculation. The diameter. Well, the diameter changes from 1.75 down to 0.4 millimeters, but I'm looking for the biggest Reynolds number, so in this case I will use the biggest diameter for the calculation. The speed can be calculated from the flow, and usually I can see that very often we can see maximal of 28 cubic millimeters per second, and it has to be divided by the area cross section. This is just the area of the circle, and we will get that the speed inside is 11.6 millimeters per second. The density for the PLA is 1240. I check on this KGM3 website, very nice website if you need any information about the density. By the way, that's my website, so you can visit it if you want to find some information about density of different materials, not only 3D printed plastic. And then about the dynamic viscosity. Well, here I check some scientific article. Here I can see the source, and I can see that for this 210, actually depends from several parameters, mostly from the temperature. It is between 70 and 500 Pascal second. And since I'm looking for the highest Reynolds, I will use here the lowest number because we have to divide with this number. Let's see the calculation. These are those numbers. Only I added these because I have to convert millimeters to meters, and then we get this number. This is very small number, 0.00035, which is much smaller than those 2300 which I mentioned earlier. What this means? First of all, the PLA is non-Newtonian fluid, so classical Reynolds limits do not strictly apply. But Reynolds number still shows that the inertial effects are negligible in this case, and during the printing the flow is extremely laminar. Also, it explains why flow is pressure controlled, And even increasing speed dramatically, the flow remains laminar, and turbulence is physically impossible in FDM extrusion. So I have the message for the Jan from Reynolds 4.0. Feel free to push further those limits, because if you're not familiar with his channels, he can print a bench in 2 minutes. I think that's his record currently. And so we will have a nice cooperation, because he will print my test object on extremely high speed, and we will use the same materials, and I will print, I don't know, bamboo or some similar generic PLA speeds, and we will compare the strength of these materials. So thank you for your attention, and let me know down in the comments, is this understandable or boring? And thank you for still watching this video, and happy printing.